Okay, we're now recording. And I'm going to try to share the screen. Okay, so we're here. We're doing 6.4. I introduced some of it yesterday on work. So Friday and Monday on work, 6.4. 6.5 Tuesday and Wednesday on average value of a function. Then we're done with the chapter. Thursday, if you want to ask me questions, you may. If not, I'll just go ahead and keep going. But our first exam is next Friday. Okay, so again, every Friday is either a quiz or exam. Quiz, another quiz today, but then exam. So for the exam, you must show up, okay, the assigned time, so you can't just watch the video. I will take attendance, all right? So you show up with your actual picture, camera on. I won't be recording. True background, have your first and last name is on my row sheet. Talk more about the test when we get closer. And you turn in all this homework. You must give me at least 70% of it in order for me to count your homework. Okay, speaking of the homework, in 6.1, I'm going to throw out problem 19. It turns out not to be that good of a problem. It was hard to find the points of intersection. You can't do it analytically. So let me double check that part. So if you already did 6.119, all I can say is good for you. It's good practice. But there's no analytic way to do that one. So yeah. Okay, so 6.1, throw out problem 19. All right, I'm going to give you the quiz. So those of you that are here synchronously, you can get your cell phones out, take a picture, or do a screenshot. Those of you watching the video, just get the video. And here we go, quiz 2. Due at 11:59 p.m. tonight. Okay, number 1. Find the volume of the solid obtained by rotating a region bounded by y equals e to the x, easy function to integrate, y equals 0, x equals -2, and x equals 2. And it says revolve about the x-axis and use the disk method. Okay, so do the disk method for this one. Here's a function bounded by y equals 0. That's the same thing as the x-axis. And x is going from -2 to 2. And you know what to do for the disk method. You're integrating pi r squared. So I'm kind of telling you some of the answer already. Number 2, use a method of cylindrical shell. So do the shell method to determine the volume if the region bounded by y equals x to the 4th, the x-axis, y equals 0, x equals 1, x equals 3, is revolved about the y-axis. So you're spinning about the y-axis, and it tells you to use the shell method. So the shell method, you're integrating what? Circumference times height. Circumference times height times thickness, but you don't have to worry about the thickness. The thickness, delta x or delta y, becomes either dx or dy. So you're basically integrating circumference times height. Right, so there we go. Open book, open note, open discussion. You can talk about it. Do it 11:59 p.m. tonight. So you have what, 14, 15 hours to do it. Plenty of time. And just like last time, take a picture on your cell phone of your work. Just click, and then, or scan it, and then email me by 11:59 p.m. tonight. Okay. So there we go. Does anybody have any quick questions about the quiz, how to do it, and so forth? So this one must be disk. This one must be shell. It's better to do it the way that's mentioned anyway. So one disk, one shell. You're integrating pi r squared. You're integrating circumference times the height. 2 pi r h, as it were. All right, so that's the quiz. All right, so we're getting back to work, literally, in the physics sense. Okay, so we had all this work equals force times distance. I gave you all of these last time. A joule in the metric system is a Newton meter. English system, a foot-pound is a pound times a foot. Force equals mass times acceleration, of which one variation of that is weight equals mg. G is acceleration due to gravity on Earth, which is pretty much where all the problems that we're doing are. 9.8 meters per second squared, or 32 feet per second squared. Okay. A kilogram is a measure of mass, measure of stuff that you have. Okay, and 1 Newton is 1 kilogram meter per second squared. Meters per second squared means meter per second, change of velocity with respect to time. And I mentioned the gorilla problem, problem 1. 360-pound gorilla moves 20 feet. 360 times 20 is 7,200 foot-pounds. Okay, so that was too easy. So what about the rest of the problems? Okay, so what makes them harder? So let's look at 3. A variable force of 5x and negative 2 pounds moves along an object which is x feet from the origin. Calculate the work done in moving the object from x equals 1 foot to x equals 10 feet. Okay. So here's the picture. The force they tell me was 5x at a negative 2. 5x at a negative 2 is the same as 5 over x squared pounds. Okay. So you're moving from 1 foot to 10 foot. How come this is not just like the gorilla problem? Work is force times distance. Well, it's because you don't have a constant force all throughout, right? So for instance, if you plug in 1, the force is 5 pounds. If you plug in the endpoint 10, 5 over 10 squared, 5 over 100, that's like 0.05. There's very little force at the end. So you do not have a constant force. So it looks like it gets easier to push as I go along. So right at the beginning, right? When I'm right over here, I need to push with 5 pounds. By the time I get to here, I just barely tap it, right? So I do not have a constant force. So how do I possibly work this out? Okay, so I do a typical slice. So here's a tiny slice. Remember, there's a whole bunch of these. So you see these little tiny slices I have here? That represents, I'm supposed to do this to the entire interval. Chop, 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 all the way throughout. Here's a typical slice. Okay, here's a delta x. Okay. And let's say this is right in the middle, 5. Okay, if delta x is really small, there's not much of a change from here to here. So what I wrote here was 5 and 5.0001. I just made that up. Those aren't any numbers that are special. But the whole idea is if you're chopping up very, very fine, these two are practically the same force. Right? So my delta W, change in work, is force times distance. Okay, so what is the force at any given point? Well, 5 over x squared, and the little change is delta x. So here's the thing. If I chop it very finely, let's say this is 5, this is 5.0001. There's not much of a difference between 5 and 5.0001 for continuous functions. It's practically the same. So if I were to take this tiny piece and move it delta x, it is like the gorilla problem. It's not quite, okay, because at the leftmost point, my force is 5, or whatever I get when I plug in 5, I should say, f of 5. And on the right endpoint, it's 5.0001, and I will plug it in. They're almost the same. So for this very tiny slice, it almost is the gorilla problem. Okay. I guess by analogy, I mean, it's even a bigger discrepancy with the gorilla. I mean, I guess you could argue the gorilla, the top of the gorilla's head, as opposed to the bottom of the gorilla's foot, they're not moving the same distance, perhaps, right? But we're pretending it's the same. I mean, this is even finer of a slice. So the change in work is the quote unquote constant force on this tiny little piece, 5 over x squared times delta x. Okay. So this becomes an integral as delta x approaches 0, n approaches infinity. What's n? The number of pieces you chop it into. That's chop, 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 all the way through. Here's a typical chop, typical slice. So as n approaches infinity and delta x approaches 0, you do have the integral. Okay, bottom line, you're just integrating the force. Okay, so I integrate from 1 to 10, 5x at a negative 2 dx. Okay, so if you didn't understand this illustration, you just, what do I do to get through the homework and the quiz and the test? Okay, you're integrating the force for this kind of a problem. So 5x at a negative 2 dx. Right? So integrate 5x at a negative 1 over negative 1 from 1 to 10. Let's see, this becomes negative 5. X at a negative 1 means 1 over x, so negative 5 over x from 1 to 10. Okay, plug in 10, I get negative 5 over 10, minus, plug in 1, I get a -5. So -1/2 plus 5. So final answer is 4.5 foot-pounds. All right, so if they give me a problem like this, you're essentially integrating a force. They may not give you the force. You'd have to figure out what the force is. Right, so that's problem number 3. Okay, 7. I'll show you 7. These problems are right off the homework. That's right. So it's a little bit less you have to do, except go back and review it. 7. A force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. How much work is done in stretching it from its natural length to 6 inches beyond its natural length? Question number 7 there. Okay, so we're doing the English system, which requires foot-pounds, but they give me stuff in inches, so I have to convert to feet. So 12 inches makes a foot. So how much is 4 inches in terms of feet? 1/3. How much is 6 inches in terms of feet? 1/2, half a foot. Right, so here's the picture. Force is 10 pounds. I'm stretching it 1/3 of a foot. And in 6 inches, half a foot. All right, so this is where we're using Hooke's law for springs. And the formula is F equals Kx. Hooke's law for you physics people, aware of that? F of x is equal to Kx, the force function. It's proportional to the distance that I am away from the home position. It's sort of like the position that the particle wants to be at for this particular spring. So here's what you do. First, I have to figure out the force. I have to figure out the K, sorry. So force is Kx. Force is 10, that goes here. X is the distance away from home in feet. So it said 4 inches, it's 1/3 of a foot, right? So 10 is equal to K times 1/3. 10 equals K times 1/3. Plug in 10 here, 1/3 here. And then I multiply both sides by 3. Tells me K is 30. So f of x is equal to Kx, f of x is equal to 30x. And now the rest of the problem is like this one. So that's what makes this problem a little bit harder. You have to figure out what that force is. F of x is equal to Kx. So you integrate the force. All right, and the second part of the problem, it says, how much work is there in going from home to 6 inches? And as we said, I have to plug in a half. It's half a foot because everything's in feet for English system here. They made me go through the trouble of doing it in inches. All right, so I'm integrating from 0 to 1/2 of 30x dx. All right, so 30x squared over 2 means 15x squared from 0 to 1/2. That's a half there. Plug in 0, you get 0. Plug in 1/2. 1/2 squared is 1/4. So 15 times 1/4 minus nothing. Final answer is 15 over 4 foot-pounds. Okay. So that's the way that one works. All right, and question 9 is similar, except they do this in the metric system. Okay, so let me show you 9. If it looks like I'm practically doing all the problems, you may be right. Okay, just so you can have it, just review it. Number 9, suppose 2 joules of work, so that automatically tells me I am in the metric system. 2 joules of work is needed to stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. Okay, this is a little tricky. The natural home position is 30. So when you're working these problems out, that's considered 0. So this is considered 0. And how far am I stretching it? To a length of 42. So distance away from home is 12 centimeters. That's the way you interpret that. So natural length is 30, home position is 30, going to 42. That really means, and by the way, this is centimeters, I have to switch it to meters, 0.3 meters to 0.42 meters. So distance away from home means you're starting at 0 and you're going to 0.12. Distance from the home position, the natural position. Okay, so you don't plug in 30. 30 is a natural position, the home position. So you're going from 0 to 0.12. Okay, and then after that, it says how much work is needed to stretch the spring from 35 centimeters to 40 centimeters. Okay, so once again, the home position is 30. So I'm not plugging in 35 and 40, and beyond that, I have to switch it to meters. Home position is 30. So 35 centimeters means 5 centimeters away from home. 40 centimeters means 10 centimeters away from home. Okay, so I'll be getting all of that there. I'm getting a message that the internet connection is unstable. So if I lose connection, then I'll try to get back on. Such is the way it is when we're teaching under COVID, right? And Zoom and all that stuff. Okay, let's see, where am I? Right, so summarizing, 30 centimeters to 42 centimeters. In meters, it's 0.3 to 0.42. 100 centimeters makes a meter, which means I divide each of these by 100, 0.3 meters to 0.42 meters. Okay, now they tell me it's 2 joules of work. So 2 is the answer to the integral. If I integrate the force. Okay, so the force is kx dx from 0 to 0.12. Okay, so again, we're going from 30 to 42 centimeters, which is from 0 meters to 0.12 meters from home. So I have to solve this for k. So 0 to 0.12, integral of k dx, that answer comes out to be 2. The total amount of work is 2 joules. So that gives me k x squared over 2 from 0 to 0.12. Plug in 0, you get 0. Plug in 0.12, I get k over 2. 0.12 squared is equal to 2. Right? Ignore this for a moment. So how do I solve this for k? I multiply both sides by the reciprocal of 0.12 squared over 2. So multiply both sides by 2. That gives me 4, right? Times 2 here, times 2 here, 4, and divide by 0.12 squared. Okay, that comes out to be 277.7 repeating. The bar, you might recall, means repeating. 277.777. That's my k. So f of x is equal to 277.7 repeating x. So now that's my force function. Now, again, it's said to go from 35 centimeters to 40 centimeters. The home position was 30 centimeters. So when I'm using the formula F equals kx, it's the distance away from home, not the distance away from the wall. So in this case, 35 centimeters, we said, was 5 centimeters away from home. 40 centimeters is 10 centimeters away from home. Again, 30 is the natural position, the home position. And change everything to meters. 5 centimeters is 0.05. 5 centimeters is 0.05 meters. 10 centimeters is 0.10 meters. So when I do the work from 35 to 40 centimeters, I'm plugging in 0.05 to 0.10. So here I go, integrate from 0.05 to 0.10 of 277.7 repeating x dx. Okay. I think the hardest part for this problem is all the conversions and how do you know what you're integrating from where to where, from this starting point to this starting point. And they have to make it harder on me to starting off in centimeters, so I switch over to meters. All right, so 277.7 repeating, that's a bar. X becomes x squared over 2. So this is 277.7 repeating divided by 2. 0.10 squared minus 0.05 squared. punch it in the calculator. It's about 1.04 joules. So the answer is 1.04 joules of work. Joules of work going from where to where? Going from 35 centimeters to 40 centimeters. And where the home position is 30 centimeters. And then part B, let's see where it go. 9B. How far beyond its natural length will the force of 30 newtons keep the spring stretched? We know the force, we know the K, so I just have to figure out the X now. So it's not even calculus, it's just a plug-in. F equals KX. Force is 30 newtons. I know the K is 277.7 repeating. Divide both sides by 277.7 repeating. I get 0.108 meters. Okay, and then here's another principle of how you present your answers in science and so on. So even though when I do the calculations, it's in meters, the original problem had everything in centimeters. Centimeters, right? So even though temporarily, to make the formulas work, I just switched to meters, my final answer is back in centimeters. So I should present the answer back as 10.8 centimeters. So that's my answer. Okay, so one more time, even though you need to do all the work in meters, you always present the answer in the same units as was given. So in a given problem, do a centimeters, centimeters, centimeters. It'd be kind of weird to leave my answer as meters. So I switch back to 10.8 centimeters. Okay. So that's the way that one works. Okay, then let's see. 13A. Where are we? 13A. Let's take a look at that. A heavy rope, 50 feet long, weighs 0.5 pounds per foot, hangs over the edge of a building that's 120 feet high. We're only doing A, not B. How much work is done in pulling the rope to the top of the building? Okay. So here's a picture. There's a rope hanging over the side, 50 feet. The building's 120 feet. That's actually immaterial. You don't really need to know that. Doesn't matter if the building's 120 feet or 1,000 feet. Well, it has to be at least 50 feet. Never hang down. Okay, so can you imagine this? Just pretend there's a rope hanging over the edge, right? And then you're going like this to bring the rope up. Can you see that? Well, it's not as simple as the gorilla problem, force times distance, because if I chop this up in a whole bunch of pieces, right? Okay, not all the rope pieces are traveling the same distance, correct? So the rope pieces at the top, they're almost already at the top, so I just tug it, it's already there. But the ones way at the bottom, there's more that you have to travel. Okay. Now, if I have to use a bad analogy, I hope you're never in this situation, but if you yourself are hanging off this rope, you would much rather be here probably than here, right? Because if you're over here, I got to reach the top. Well, I'm almost already at the top. But if you're down here, there's a lot more climbing you got to do, right? So in a strange sense, these rope pieces have to climb higher than the ones that are right at the top. They're practically already at the top, but the rope piece at the bottom is a little bit more. Not to mention you have all the weight at the bottom. Okay. And if you can imagine a scenario of this rope, this heavy rope at the bottom, you have to tug more at the bottom, right? But as you draw more and more of this rope, it gets easier and easier because there's less rope that you have to pull up, right? And yes, at the beginning, you got to pull the whole rope up. Well, the ones that's already almost at the top, they're done, right? They're home free, they're safe, quote unquote. But then the rope pieces way at the bottom, you got to do more right? To get it all the way up. All right, so how do I think of this problem? Again, I slice delta x. Here we are. And here's the nice thing again. For this very small delta x, all these rope pieces are traveling just about the same distance. Yes, you could argue, well, at the very top of that slice, it's going a little bit less than the very bottom of the slice. Okay? I only draw this slice. Remember, it's really slice, 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 chopping it up into a million pieces, and delta x is very, very tiny. Okay? And as delta x approaches 0, the approximation gets better and better and better to the point where it becomes an integral. Right. So for this very tiny slice right here, it's the gorilla problem. Force times a constant distance. Okay? Not really constant because the rope piece at the top is a little bit less than rope pieces on the bottom. But if you slice very small, it is like the gorilla problem, essentially. Like it's probably better than the gorilla problem because the gorilla, we were assuming, the top of the gorilla's head and the bottom of the foot are traveling the same distance. And that's not necessarily the case. So this would actually be a more accurate representation, I suppose, of constant force times constant distance. All right, so I call this x equals 0. If you're at the top, you have to travel nothing. Here's x equals 50. At the bottom, you have to travel 50 feet. This is delta x, and this is my x. So up here, x equals 0, x equals 1, x equals 2. So let's say this is halfway, then all of these rope pieces have to travel 25 feet. All right, so how do I get the change in work? And this is where I analyze my units. You science people, physics people know about canceling units, get units to line up the right way, so to speak. All right, I'm told it's 0.5 pounds per foot. How much is this slice? Delta x feet. So how much does this slice weigh? 0.5 delta x. Feet cancels out. Right? So this tiny slice has a weight of 0.5 delta x pounds. The density is 0.5 pounds per foot. How many feet do I have? Delta x. Notice feet cancels out. So right now I have pounds. This weight is traveling the same distance up, x feet. So now I have foot pounds, and that's what I want. My change in work, delta W, is now in foot pounds. So 0.5x delta x foot pounds. My delta W, change in work. So the work required to take this slice to the top is force times distance. Force is 0.5 delta x. Force is the weight. And the distance that all of these rope pieces are traveling is x. So for this tiny little slice, it is like the gorilla problem. Constant force, constant distance, although we know that the distance is not quite constant for the top and the bottom, but as delta x approaches 0, the approximation gets better and better to the point of becoming an integral. All right, so to find the actual work, I integrate, delta x becomes dx, 0.5x dx. Okay, so we're pretty much there. So 0.5 x squared over 2 from 0 to 50. 0.5 over 2, plug in 0, you get 0. Plug in 50, you have 50 squared. So 0.5 over 2 times 50 squared, punch it in your calculator, 625 foot-pounds. Okay, so that's the way that one goes. Okay, 15, I was going to give you the setup, but I wasn't going to do the whole thing. Otherwise, I'd almost literally be doing all the problems. I might end up showing it to you anyway. Let me give you the setup for 15. A cable that weighs 2 pounds per foot is used to lift 800 pounds of coal up a mine shaft 500 feet deep. Find the work done. Okay, so the density is 2 pounds per foot. There's 800 pounds of coal, and there's a cable that's pulling it up. find the work done. Okay, so I'm going to show you just this part. I got some other stuff there, but I wasn't really going to show it to you. Although I guess if you look at the video quickly, I've already done it. So here's what's happening. 500 feet down a coal mine shaft, there's 800 pounds of coal at the bottom, right? The cable weighs 2 pounds per foot. And here's my slice delta X. So you can split this into two parts. The coal at the bottom, 800 pounds, it all has to go up 500 feet. That is the gorilla problem. So the work for the coal is just like the gorilla problem, force times distance. The cable part, that looks exactly like this one we just did. Just a different density and a different distance, and that'll do it. So I'll just mention for 15, and if I have time, maybe I'll show it to you next time, but the setup is break it into two parts. You lift in the coal at the bottom. Constant force, 800 pounds. Constant distance, 500 feet. So just multiply them. Then you have to bring the cable up. Work this out just like the rope problem. Exactly the same. Now over here it was what, 50 feet? Here it's 500 feet. Here it was 0.5 pounds per foot. This one is 2 pounds per foot. So break it in two parts. Work for the coal is like the gorilla problem. Work it out just like that. And then the work for the cable. Okay, so I'm going to cover, I'm trying to cover it up. Find the work for the coal, W coal, and the work for the cable. This one is just like the gorilla. Maybe I'll even put that here, like gorilla problem. And the work for the cable is like number 13. So I'll just see like number 13. Okay. Work for the coal, gorilla. Work for the cable, work it out like this one, number 13. Okay. That's the setup that I want to give you. Okay. I was almost done. Let me give you a setup for 21 because there's a lot of work involved. Sorry, not the physics work, but the ordinary English work idea for 21. An aquarium 2 meters long, 1 meter wide, and 1 meter deep is full of water. Find the work needed to pump half the water out of the aquarium. And it says the density of water is 1,000 kilograms per meter cubed. Okay, so I'll just give you the setup. Let's see, we have about 15 minutes left. So I won't be able to do the problem in its entirety. Let me just give you the setup of what this is. Now, I'm going to change the problem actually a little bit. It says 2 meters by 1 meter by 1 meter, pump out half the water. If I do that, why don't I just pretend it's 2 meters by 1 meter by half a meter and pull out all the water? Does that make sense? Okay. If I have half the water, then I'm only taking out half a meter deep. So I'm going to change the problem so that it's 2 meters by 1 meter by half a meter and pull out all the water. So the picture is like this. 2 meters, 1 meter, half a meter. Pulling out all the water. Okay. I'm slicing like so. It's almost like I got a very thin sandwich of water. And you say, why am I slicing like that? If I slice like this, all the water molecules on this slice are traveling the same distance roughly. which is X. Your internet connection is unstable. Okay, we try to get this done right away. All right, so you've got this suction taking out the water. Again, not all the water molecules are traveling the same distance. If you're very close to the top, yeah, we're making the assumption that this suction is always pulling from the top, not all the way to the bottom. I know real aquarium filters, and some of you know this better than I. You just put it at the bottom. That's kind of a waste because you're making all the water go up. More efficient is if you have this hose, the suction, just right at the top. And as the water goes down, the suction goes down with it. So the water molecules don't have to travel as far as all the way to the bottom in each case, right? So I'm saying for this thin slice, all the water molecules are traveling the same distance, in this case, X. All right, so here's my setup. I have 1,000 kilograms per meter cubed. I can find the volume of that slice. It's 2 meters by 1 meter by delta X meters. I don't put a half. Okay, just for this slice, that very thin sandwich of water, all of those water molecules are traveling the same distance. So I'm trying to turn it into the gorilla problem for this slice: constant force, constant distance. Okay. And here's how you set up the units analysis. See, I have a meters cubed in the bottom. So I say to myself, how do I get rid of the meters cubed? I need a meters cubed on top, a meter, meter, meter. So 1,000 kilograms of meters cubed, 2 meters by 1 meter by delta X meters. And now the meters cubed cancels out. Meters cubed, meter, meter, meter cancels out. So now I just have kilograms in terms of units. Transform that into a weight, 9.8 meters per second squared. So now that's a force. Work is force times distance. How far are these water molecules traveling? X meters. X meters. So I have a force times a distance. Okay. At the top, it's almost nothing. At the bottom, it's half a meter. Okay. In general, wherever I am, it's X meters. Okay, so one more time. Density, 1,000 kilograms of meters cubed, multiplied by the volume, 2 meters by 1 meter by delta X meters. Meters cubed here, Kansas meters cubed here. I now have kilograms. That's a mass. Multiplied by the acceleration due to gravity, 9.8 meters per second squared. Put this on your cheat sheet if you want. And now all of this right here is newtons. Newtons times meters is Newton meters or joules. Okay, so then I multiplied 1,000 times 2 times 9.8, 19,600 X delta X joules. That's how I set up my delta W. Change in work. Okay, and that's what I integrate. Force times distance. Okay, delta X in the integral becomes dx. So I'm essentially just integrating 19,600. I'm already here, I might as well just finish it. Okay, so you're going from 0 to 1/2. So I integrate 19,600 X dx. 19,600 X squared over 2. From 0 to 1/2. 19,600 divided by 2 is 9,800. Plug in 0, you get 0. Plug in 1/2. 1/2 squared is 1/4. Punch it in your machine. 2,450 joules. So the answer is 2,450 joules. So this aquarium, to slice this way, so how come I don't slice this way, go up and down? That's because those water molecules are not traveling the same distance. Okay, for a slice like so, this sandwich of water, so to speak, they're all moving the same distance, X. So they gave me the density, change it to mass. I had to get rid of meters cubed. Meters cubed in the bottom means I needed meters cubed on top. So meter times meter times meter, volume. Then I have kilograms, multiplied by the acceleration due to gravity on Earth. So right up to here, this is force, and then this is the distance. Punch it in your machine. 19,600 x delta x joules. That's what I integrate. Delta x in the integral becomes dx, 19,600, and the rest is plug-in. Okay. All right, I am done, folks. So let me see if I can check the chat. It's about 8:50. Let me see the chat. Okay, so you've got your quiz due at 11:59 p.m. tonight. First one is this method. Second one is the shell method. Open everything. You can talk about it. You can help each other out. Look in your book, look in your notes, and submit it by 11:59 p.m. tonight. Okay, so anybody with any questions? Otherwise, we're done, folks.
Yeah, I got just a question for you. I was gonna ask you about an office hour, but yeah.
Okay, I can barely hear you. Say it again, or else type it in the chat.
Yeah, here, hold on.
Okay, meantime, anybody else have a question?
Can I just stay a little bit afterwards to ask you some questions about the course?
Sure, you can.
Thank you.
Anybody else? Okay, well, folks, we're essentially done. So if you have no other questions, you're free to leave and have a good weekend. And I'll wait to get your response in the quiz. Okay, I'm going to stop the recording. So. Okay, yeah, let me stop the recording here.